The morning of January 7th, 1945. Leyte Gulf, Philippine Islands. First Lieutenant Robert McClurg tightened his harness straps and pushed the F4U Corsair's throttle forward. The Pratt & Whitney R2800 engine roared to life, vibrating through the aircraft's frame as he began his takeoff roll from Tacloban airfield. Above him, the sky held a formation of Japanese A6M0s, 20 or more, diving toward American positions with tactical precision. McClurg had flown 43 combat missions, and he understood the mathematics of aerial combat better than most pilots in VMF 218. But what he was about to demonstrate would fundamentally alter Japanese tactical doctrine for the remainder of the war. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Corsair accelerated, its inverted gull wings cutting through the humid Pacific air. McClurg climbed, aggressively, his eyes tracking the enemy formation. Within minutes, he had positioned himself for an intercept, rolling the Corsair into a tight defensive turn as a Zero pilot attempted to gain position. The G-forces pressed McClurg deep into his seat. His vision began to narrow at the edges, peripheral awareness fading to grey as blood drained from his retinas. But he held the turn, his muscles tensed, jaw clenched, pulling the Corsair through 7 full Gs of sustained force. The Zero pilot tried to follow. He could not. The Japanese fighter's wings began to flex dangerously at 6 Gs. Structural limits screaming through airframe components never designed for such punishment. The Zero pilot had no choice but to ease off, to reduce his turn rate, to accept a wider radius. In that moment, the tactical advantage shifted irrevocably. What McClurg and thousands of other Corsair pilots were exploiting was not superior piloting skill alone, though that mattered. They were exploiting a fundamental engineering disparity that Japanese designers could never overcome. The F4U Corsair had been built to withstand sustained forces that would literally tear a Zero apart in mid-air, and Japanese pilots, flying aircraft that prioritized maneuverability over structural strength, found themselves trapped in a lethal paradox. They could turn tighter at moderate speeds and low G loads, but the moment an engagement intensified into high G combat, their aircraft became death traps. The disparity between American and Japanese fighter design philosophy emerged from fundamentally different strategic requirements and industrial capabilities. When the Imperial Japanese Navy issued specifications for what would become the A6M0 in 1937, they demanded the impossible. The aircraft needed to function as an interceptor, a dogfighter, and a long-range escort, all while operating from carriers with limited deck space. Range was paramount. Japanese strategists understood they would be fighting across the vast expanses of the Pacific, far from secure bases. The Zero needed to escort bombers on missions, measuring over 1,000 miles round trip. This requirement forced designer Jiro Horikoshi into brutal compromises. To achieve the necessary range, the Zero had to be light, extraordinarily light. Every kilogram of structural weight reduced range, so Horikoshi stripped away everything not absolutely essential to flight. Armor plating for the pilot? Eliminated. Self-sealing fuel tanks? Too heavy. Even the radios were substandard, often removed by pilots to save additional weight. The Zero's airframe was constructed using a revolutionary integral wing design, where the fuselage and wings formed a single structural unit. This method, slower and more labor-intensive than American techniques, produced an aircraft with remarkable rigidity at low stress levels. But it came with a critical limitation. The Zero was designed to a load factor of 6 Gs normal operation, with an ultimate failure point around 12 Gs including safety margins. This meant a Zero pilot could safely pull 6 Gs without damaging the aircraft. Between 6 and 12 Gs, the airframe would survive but likely sustain structural damage. Above 12 Gs, catastrophic failure became probable. Wings could separate from the fuselage, control surfaces could rip away, the entire aircraft could disintegrate in mid-air. Japanese test documents from the Plains of Fame Air Museum, which operates an authentic A6M5, confirmed these specifications. The museum's restoration team, working directly with original designer Jiro Horikoshi in the late 1970s, verified that the structural limitations were intentional. 6 Gs was considered adequate for combat maneuvering in 1940 when the Zero entered service. Most combat occurred below 300 miles per hour, where sustained high G turns were rare. The Zero's legendary maneuverability came from its low wing loading, meaning the aircraft's weight was distributed across a large wing area. This gave it an extraordinarily tight turn radius at moderate speeds. At 180 to 280 miles per hour, the Zero could outturn virtually any fighter in the world. It could roll into a turn and complete a full circle, while American fighters were still halfway through their own turns. Japanese pilots exploited this advantage ruthlessly in the war's early years, forcing American pilots into turning fights where the Zero's agility dominated. But that advantage evaporated above 325 miles per hour. At higher speeds, the Zero's controls stiffened dramatically to prevent wing failure. The control surfaces, lacking hydraulic assistance, required so much physical force to move that pilots couldn't execute rapid maneuvers. And pulling hard turns at high speed generated G-forces the airframe simply couldn't handle. American test pilots who evaluated captured Zeros noted that the controls were, quote, very light at 200 miles per hour, but stiffened at speeds above 216 miles per hour to safeguard against wing failure. This was a design feature, not a defect. Japanese engineers understood that if pilots could easily move the controls at high speed, they might inadvertently exceed structural limits and destroy their own aircraft. The Chance Vought F4U Corsair represented a completely different design philosophy. When Vought engineers began work in 1938 on what would become the Corsair, they had one overriding mandate: build the fastest, most powerful fighter possible. The United States Navy wanted speed above all else, and Vought delivered. The design team, led by Rex Beisel, selected the largest, most powerful engine available, the Pratt & Whitney R2800 Double Wasp, an 18-cylinder radial producing over 2,000 horsepower. This engine was nearly twice as powerful as the Zero's 950 horsepower, Nakajima Sake. But that enormous power created engineering challenges. The engine required a massive propeller to absorb all that horsepower, a Hamilton Standard unit measuring 13 feet 4 inches in diameter, the largest ever fitted to a single-engine fighter at that time. To provide ground clearance for such a huge propeller, the landing gear would need to be impossibly long and structurally weak. Vaught's solution was the inverted gull wing, the Corsair's most distinctive visual feature. By angling the wing downward at the fuselage junction, then upward toward the tips, designers positioned the engine high enough for propeller clearance while keeping the landing gear reasonably short and strong. The inverted gull configuration served multiple purposes beyond propeller clearance. It allowed the wing to meet the fuselage at an optimal angle for minimizing drag. It positioned the landing gear attachment points lower on the wing structure, where forces could be absorbed more effectively. And critically, it created an exceptionally rigid structural assembly. Vought built a special large jig that enabled the wing's center section and lower fuselage to be constructed as a single, integrated unit. This technique produced what engineers described as an, quote, extremely strong structure. The Corsair's wings and fuselage junction could withstand forces that would shatter less robust designs. The aircraft was stressed to 8 Gs normal load factor, with a 50% safety margin providing 12 Gs ultimate load. In practical terms, a Corsair pilot could pull 8 Gs repeatedly without causing any structural damage whatsoever. Between 8 and 12 Gs, the aircraft would survive, but might sustain some deformation. Only above 12 Gs did catastrophic failure become likely, and 12 Gs represented forces almost impossible for a human pilot to sustain consciousness through anyway. The Corsair's construction incorporated 150 pounds of armor, plate protecting the pilot and critical systems. A 1.5-inch bulletproof windscreen, set internally behind curved plexiglass, provided frontal protection. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Self-sealing fuel tanks prevented catastrophic fires from gunfire. The entire aircraft was engineered to absorb punishment and keep flying. Corsairs routinely returned to base with battle damage that would have destroyed Zeros. Pilots reported Corsairs landing safely with holes you could put your fist through, with sections of tail surfaces shot away, with damaged control systems still providing enough authority for controlled flight. This durability came at a cost. The Corsair weighed approximately 9,700 pounds empty, compared to the Zero's 3,960 pounds. The American fighter was nearly 2.5 times heavier, but that weight was transformed into lethal kinetic energy in a dive, and it provided the structural mass necessary to sustain high-G maneuvering without airframe. Failure. When American pilots first encountered Zeros over the Pacific in 1942, they faced a fighter that seemed supernatural in its agility. Wildcats and P-42s couldn't turn with Zeros at low speeds. American pilots who tried to engage in traditional dogfights found themselves quickly outmaneuvered, presenting vulnerable aspects to Zero guns, and dying. The losses mounted through the first 6 months of the war. American tactical doctrine had to change, and it changed through painful trial and error paid for in blood. Pilots like Lieutenant Commander John Thatch developed the Thatch Weave, a defensive tactic where two fighters covered each other, preventing Zeros from exploiting their turn advantage. But defensive tactics only prevented losses. They didn't win battles. The Corsair's arrival in combat in February 1943 began to shift the balance. Marine squadrons operating from Guadalcanal received the first combat Corsairs, and pilots immediately recognized they had an aircraft that could dictate engagement terms. The Corsair was 50 miles per hour faster than early model Zeros, topping 400 miles per hour in level flight. It could outclimb the Zero by a significant margin. And crucially, its rugged construction meant Corsair pilots could execute aggressive maneuvers without fearing structural failure. Early Corsair pilots developed boom and zoom tactics. Dive from altitude at high speed, make a single firing pass, then extend away using superior speed before the Zero could turn to engage. If a Zero tried to pursue in a dive, the Corsair would simply pull away. Zero pilots found their speed advantage evaporating as Corsairs disappeared into the distance. But zoom and boom tactics, while effective, limited tactical flexibility. They worked best when the Corsair pilot had altitude advantage and could choose when to engage. If combat devolved into a sustained turning fight at lower altitudes, the Zero's tighter turn radius still provided advantages. Until pilots discovered that the Corsair's structural strength enabled a completely different approach: high-G sustained turning. The human body's response to G-forces had been documented as far back as World War I, when pilots reported fainting in the air during tight maneuvers. By the 1920s, RAF pilots competing in Schneider Trophy air races experienced blackouts, leading officials to restrict turns to 4 Gs, to limit pilots to greyout with only partial vision loss. But understanding the problem didn't immediately solve it. During the Battle of Britain, an estimated 30% of pilot deaths resulted from accidents, including blackouts during high-G maneuvering. Supermarine Spitfires were capable of rapid turns, generating forces that caused pilots to lose consciousness when diving to fire or evading enemy fire. The physiological mechanism was well understood by 1940. When an aircraft executes a tight turn, centrifugal force pushes the pilot downward into his seat. This force, measured in Gs, acts along the vertical axis of the pilot's body. At 2 Gs, the pilot feels twice his normal body weight, pressing him into the seat. His heart must work twice as hard to pump blood up to his brain against this increased gravitational pull. At 3 Gs, the difficulty triples. An 80-kilogram pilot pulling 7 Gs experiences forces equivalent to 560 kilograms pressing down on his body. The cardiovascular system begins failing under these conditions. The heart struggles to maintain sufficient blood pressure to perfuse the brain. Blood pools in the lower extremities. Capillaries in the legs and abdomen dilate from the increased pressure, holding blood that should be circulating. The first symptom is greyout, a dimming of vision accompanied by loss of color perception. Peripheral vision fades as retinal blood pressure drops below the threshold needed to supply the edges of the visual field. If G-forces continue, tunnel vision develops. The pilot can see only what's directly ahead, his peripheral awareness completely gone. Then, blackout occurs. The pilot loses all vision, but remains conscious. He can think, he can hear, he can feel the controls, but he cannot see anything. If forces continue beyond blackout, G-induced loss of consciousness, or G-lock, occurs. The pilot completely loses consciousness, typically for 12 to 15 seconds. During that time, nobody is flying the aircraft. When consciousness returns, there's a period of disorientation, often lasting 15 to 30 additional seconds, during which the pilot cannot function normally. Brief, vivid dreams sometimes accompany the unconscious period. Myoclonic convulsions, uncontrolled muscle-jerking pilots nicknamed the funky chicken, often occur during recovery. Trained fighter pilots learned to recognize the warning signs. Experienced aviators could feel grey-out beginning and would reduce G-forces before reaching blackout. They developed techniques to extend their tolerance. Tensing the abdominal muscles and leg muscles created resistance to blood pooling. Grunting or yelling increased chest pressure, helping maintain blood pressure. Short, quick breaths, rather than holding breath, prevented pressure from dropping too rapidly. These techniques, collectively known as the anti-G straining maneuver, could extend a pilot's tolerance by 1 to 1.5 Gs. A pilot who would normally black out at 5 Gs might sustain 6 Gs using proper technique, but these were marginal improvements. Against determined opponents, every fraction of a G mattered. The development of pressure suits began during World War II. Professor Frank Cotton at Sydney University designed the first successful gas-operated anti-G suit in 1941. His design used rubber sacks covered externally by inextensible material that automatically inflated when G-forces increased, squeezing the legs and abdomen to prevent blood from pooling. American researchers at the Mayo Clinic, led by physiologists Earl Wood and Edward Baldes, refined Cotton's design. They recognized that maintaining arterial pressure rather than venous return was the key to preventing consciousness loss. Their GPS gradient pressure suit Type G1 entered service with American fighter pilots in late 1943. The suit added approximately 1 G of tolerance. A pilot who could sustain 5 Gs without the suit might manage 6 Gs wearing it, assuming he also used proper anti-G straining technique. But even with pressure suits and training, human tolerance remained limited. Most pilots could sustain roughly 6 Gs before experiencing vision loss. 7 Gs pushed the limits even for well-trained aviators. Above 7 Gs, blackout became nearly inevitable for all but the most exceptionally conditioned pilots, and G-suits weren't universally available in 1943 and 1944. Many Marine Corsair pilots flew, without them, relying entirely on physical conditioning and technique. This created a critical tactical bottleneck. If a Corsair pilot wanted to exploit his aircraft's superior structural strength by pulling harder turns than Zero pilots could match, he had to remain conscious while doing it. The aircraft could handle 8 Gs, sustained indefinitely. The pilot could not. Japanese pilots faced identical physiological limitations. Their bodies responded to G-forces the same way American pilots' bodies did. But they flew aircraft that imposed structural limits below human limits. A Zero pilot pulling 6 Gs was approaching his aircraft's safe operating threshold. If he pulled harder, he risked structural failure. Japanese training emphasized smooth, coordinated maneuvers rather than violent high-G turns. Pilots learned to use the Zero's natural agility, its tight turn radius at moderate G loads, rather than attempting to muscle through high-stress turns that might break the aircraft. In early war combat, this approach worked. Most engagements occurred at speeds where the Zero's maneuverability advantage dominated. American fighters that tried to turn with Zeros at moderate Gs found themselves outmaneuvered regardless of structural strength. The solution wasn't pulling harder Gs, it was refusing to fight on Japanese terms. But as the war progressed and Corsair pilots accumulated combat experience, a new tactical approach emerged. If the engagement geometry prevented boom and zoom tactics, if combat devolved into a sustained turning fight, Corsair pilots discovered they could pull harder sustained turns than Zero pilots could follow without destroying their aircraft. The key was managing one's own physiology, while exploiting the enemy's structural limitations. Lieutenant Robert McClurg's engagement on January 7, 1945, demonstrated this principle perfectly. When the Zero pilot attempted to follow McClurg's 7G turn, he couldn't maintain the same turn radius without overstressing his airframe. The Zero's wings began flexing, visible oscillations that any experienced pilot would recognize as imminent structural failure. The Japanese pilot had two choices: reduce his G loading and accept a wider turn radius, allowing McClurg to gain angles, or maintain the turn and risk his wings separating from the fuselage. There was no third option. Japanese engineering had imposed limits that no amount of pilot skill could overcome. The tactical implications were profound. In the war's early years, American pilots avoided turning fights because Zero agility dominated at moderate Gs. But by 1945, Corsair pilots actively sought turning engagements, knowing they could exploit structural superiority. If a Zero tried to match a Corsair's sustained 7G turn, the Zero would break first. Its wings would fold, its control surfaces would fail, the aircraft would come apart, and Zero pilots knew this. They'd been briefed on structural limitations. They'd witnessed aircraft disintegrating when pilots overstressed them, so when a Corsair rolled into a high G turn, Japanese pilots had to break off, had to accept defeat in that engagement, had to seek separation, and hope to reset for another pass. This psychological dimension mattered as much as the physical reality. Japanese aviators, already demoralized by mounting losses and dwindling resources, found themselves flying aircraft that couldn't compete structurally with American fighters. The Zero's legendary maneuverability, which had dominated Pacific skies in 1942, became irrelevant when combat intensified beyond 6 Gs. Let me continue with more of Part 1, as we haven't reached the output limit yet. The physiological training American pilots received improved throughout the war. By 1944, fighter tactics courses emphasized anti-G straining technique. Instructors taught pilots to tense abdominal muscles violently, grunt or yell to maintain chest pressure, and take short, rapid breaths rather than holding their breath. They practiced these techniques on the ground until they became automatic. The goal was muscle memory, unconscious responses that would activate during combat without requiring conscious thought. Combat was already cognitively overwhelming. Pilots tracked multiple enemy aircraft, managed their own aircraft's energy state, monitored fuel and ammunition, communicated with wingmen, and made split-second tactical decisions. They couldn't afford to consciously think about anti-G technique. It had to be automatic. Some pilots proved naturally more G-tolerant than others. Physical fitness mattered. Pilots with strong cardiovascular systems and well-developed leg and core muscles could sustain higher Gs longer. But genetics played a role too. Some individuals had cardiovascular systems that responded better to G-stress, maintaining blood pressure more effectively under high loading. These, naturally, gifted pilots could pull Gs that would black out their squadron mates. But even the most G-tolerant pilot had limits. 7 sustained Gs pushed everyone to their edge. 8 Gs was beyond sustainable for all but brief moments. The difference between a typical pilot and an exceptional one might be 30 seconds of sustained 7G turning versus 20 seconds. Marginal. But in combat, 30 seconds could mean the difference between achieving a firing solution and becoming a target yourself. The Corsair's pilot seat was raised 7 inches higher than earlier models to improve visibility over the long nose. This modification, introduced in the F4U variant, had an unintended benefit for G tolerance. The higher seating position reduced the vertical distance from the pilot's heart to his brain, making it slightly easier for the cardiovascular system to maintain cranial blood pressure under high Gs. The difference was small, perhaps a few percentage points, but fighter combat was a game of margins. Any advantage mattered. The raised seat also improved the pilot's ability to maintain visual contact with enemy aircraft during high G turns. When pulling heavy Gs, pilots' heads were forced backward and downward by the forces. The higher seat position meant pilots could maintain forward vision with less neck strain, keeping track of targets and threats while maneuvering violently. The tactical evolution occurred gradually across 1944 as more Marine and Navy squadrons transitioned to Corsairs. Squadron ready rooms became laboratories for tactical development. Pilots who'd survived engagements debriefed their experiences, discussing what worked and what didn't. Successful techniques spread through informal networks. A pilot from VMF 214 would share tactics with a friend in VMF 213, who'd modify the approach and pass it along to VMF 218. This organic tactical evolution, driven by pilots rather than staff officers, produced doctrine that actually worked in combat. Traditional military hierarchies struggled with bottom-up innovation. Officially approved tactics manual took months to update, but pilots couldn't wait for official doctrine. They needed techniques that worked right now, today, in the next mission. So they developed their own approaches and shared them directly. High-G turning tactics required specific setup conditions to work effectively. A Corsair pilot couldn't simply pull maximum Gs randomly and expect success. The maneuver required energy management, situational awareness, and precise timing. First, the pilot needed adequate airspeed, too slow, and the aircraft would stall before reaching high G loads. Too fast, and control forces became excessive even with the Corsair's hydraulically boosted systems. The optimal speed range for sustained 7G turns was between 280 and 350 miles per hour. Within that envelope, the Corsair could sustain maximum G without stalling or exceeding control authority. Second, the pilot needed sufficient altitude. High G turns bled energy rapidly. An aircraft pulling 7 Gs in a level turn lost airspeed at an alarming rate. Starting with 3,000 feet of altitude provided cushion. If the turn depleted too much energy, the pilot could convert altitude back into speed by accepting a descent. Starting low, below 1,000 feet, made high-G sustained turns dangerous. If energy bled away completely, the aircraft would stall with insufficient altitude to recover. Third, the pilot needed to track the enemy's position throughout the maneuver. This sounds obvious, but in practice it was extraordinarily difficult. During a 7G turn, peripheral vision disappeared entirely. Tunnel vision reduced situational awareness to a narrow cone directly ahead. The enemy aircraft, unless it was exactly where the pilot was looking, could disappear from view. Pilots had to develop spatial memory, remembering where the threat was based on the last glimpse before vision collapsed, then maintaining that mental picture during the blind period. Fourth, the pilot needed a wingman. Solo high-G maneuvering was suicidal. While one pilot executed the sustained turn, his wingman had to maintain visual contact, call out threats, and prevent other enemy aircraft from exploiting the lead's reduced awareness. The Corsair operated most effectively as an element of two aircraft, mutually supporting, covering each other's vulnerabilities. These requirements meant that high-G turning tactics worked best in specific situations. When a Corsair element encountered a smaller number of zeros, typically 2 against 4 or fewer enemies, when altitude was adequate, when airspeed was in the optimal range, and when tactical geometry favored sustained maneuvering rather than boom and zoom attacks. Those conditions didn't occur in every engagement, but when they did, Corsair pilots exploited them ruthlessly. The Japanese response to these tactics evolved through 1944 and into 1945. Intelligence officers, analyzing combat action reports and interrogating captured documents, identified the pattern. American fighters were pulling sustained high-G turns that Zero pilots couldn't match. Japanese tactical directives changed accordingly. Orders went out across all naval aviation units. Avoid sustained turning engagements with Corsairs and Hellcats at all costs. The new doctrine emphasized hit-and-run attacks, diving from altitude to make a single pass, then extending away at maximum speed. Japanese fighters were instructed never to attempt matching American sustained turn rates above 6 Gs. If a Corsair or Hellcat rolled into a high-G turn, the proper response was to break off, extend to safe distance, reset the engagement geometry, and attack from a different angle. This tactical shift acknowledged an uncomfortable reality that Japanese aviation had lost the technical arms race. The Zero's design, optimized for 1937 specifications, couldn't compete against American fighters designed with combat experience incorporated into their requirements. Japanese engineers understood the problem. They developed improved fighters like the Kawanishi N1K Shiden and the Mitsubishi J2M Raiden, both featuring more robust construction and more powerful engines. But industrial capacity limitations meant these newer types never reached frontline units in sufficient numbers. The vast majority of Japanese fighter pilots flew Zeros throughout the war, aircraft that were fundamentally outclassed by 1944. The operational reports from Marine Corsair squadrons in 1945 reflected the changing dynamics. Kill ratios improved dramatically. Where early war engagements might result in 1 or 2 Japanese aircraft destroyed for each American loss, by 1945 Corsair units were achieving 5-to-1, 10-to-1, sometimes 20-to-1 kill ratios. Black Sheep Squadron, reformed under Major Gregory Pappy Boyington, shot down 97 Japanese aircraft while damaging 103 more during 2 6-week combat tours. Their losses were minimal by comparison. Individual pilots racked up multiple kills in single missions with increasing frequency. The high-G turning tactic contributed to this success, though it was far from the only factor. Better training, superior numbers, improved tactics, and declining Japanese pilot quality all played roles. But the structural strength advantage removed one of the Zero's last remaining assets. Japanese pilots couldn't even rely on maneuverability anymore, not when American fighters could outturn them through sheer brute force and structural superiority. The physical toll on Corsair pilots who regularly pulled high Gs was significant but manageable with proper training and conditioning. Pilots reported muscle soreness in their core and legs after intensive combat missions involving multiple high-G maneuvers. The sustained tensing required for anti-G straining was exhausting. Some pilots described feeling physically drained after missions, even when the flight duration was relatively short. But this was preferable to being shot down. The temporary physical discomfort was a small price for tactical superiority. Medical officers at forward bases monitored pilots for G-related injuries. The most common issues were minor hemorrhaging in the eyes, petechiae, small red spots caused by capillaries rupturing under stress. These usually resolved within days without treatment. More serious complications were rare but documented. Some pilots experienced temporary vision problems, minor retinal damage from repeated high-G exposure. A few reported persistent back and neck pain from the cumulative stress of violent maneuvering. The Navy and Marine Corps took these health concerns seriously enough to mandate rest periods for pilots who'd flown intensive combat tours. After 6 weeks of daily combat missions, pilots were rotated to rear areas for recovery and retraining before returning to frontline units. This rotation system, while reducing available pilot strength in the short term, maintained long-term combat effectiveness by preventing physical and psychological burnout. Japanese pilots received no such consideration by 1945. Desperate for experienced aviators, the Imperial Japanese Navy kept pilots in combat continuously until they were killed or wounded too severely to fly. This policy accelerated the decline in Japanese aviation quality. Even skilled pilots became less effective when exhausted, stressed, and operating without adequate rest or maintenance support. The Corsair's maintenance requirements, while demanding, were manageable for American logistics. The aircraft's rugged construction meant it could sustain battle damage and remain operational. Maintenance crews at forward airfields became expert at field repairs, patching, bullet holes, replacing damaged components, keeping aircraft flying despite harsh conditions. The inverted gull wing's robust structure meant that even when damaged, the wing typically retained sufficient strength for continued operations. Corsairs returned from missions with significant wing damage, holes and tears from enemy fire, yet the structural integrity remained adequate for controlled flight and landing. This damage tolerance was a direct result of the over-engineering that made high-G maneuvering possible. By contrast, Zero maintenance became increasingly problematic as Japanese logistics collapsed. Spare parts shortages meant damaged aircraft sat unflyable on dispersal areas, waiting for components that never arrived. Japanese maintenance personnel possessed the skill to repair aircraft, but lacked the materials. American submarine warfare had severed supply lines, preventing raw materials from reaching Japanese factories and finished parts from reaching combat units. Zero's lightweight construction, while enabling its impressive range and agility, made it vulnerable to damage and difficult to repair under field conditions. The integral wing construction that provided structural strength at low G loads also meant that significant wing damage often rendered the entire aircraft unflyable. American spot-welded construction allowed damaged sections to be cut out and replaced. Japanese construction techniques made such repairs far more difficult. The strategic implications of the Corsair's high-G capability extended beyond individual engagements. American air superiority over the Pacific became absolute by early 1945. Japanese aircraft could barely contest American operations. Carrier strikes against Japanese home islands encountered minimal effective resistance. Kamikaze attacks, desperate suicide missions, represented Japan's acknowledgement that conventional fighter tactics had failed. If your pilots can't survive combat against superior American fighters, use them as guided missiles instead. The logic was brutal, but consistent with Japanese desperation. The high-G turning tactic contributed to this strategic situation by removing the last vestiges of Japanese fighter effectiveness. Even when Japanese pilots managed to intercept American formations, even when they achieved favorable tactical positions, they couldn't exploit opportunities because their aircraft couldn't sustain the maneuvering required. One particular engagement from March 1945 illustrated the tactical dynamic perfectly. Lieutenant James Swett of VMF 221, already an ace with multiple confirmed victories, encountered a formation of 6 Zeros while flying combat air patrol over Okinawa. Swett was alone, his wingman having returned to base with mechanical issues. 6 against 1 should have favored the Japanese, especially given the Zero's reputation for maneuverability. Swett used his altitude advantage to dive on the formation, destroying 1 Zero in his initial pass. The remaining 5 Zeros converged on him, attempting to use their numbers to overwhelm the single Corsair. Swett rolled into a sustained 7G turn, using his aircraft's structural strength to maintain a turn radius the Zeros couldn't match without exceeding their airframe limits. The Japanese pilots tried to follow. 2 of them pulled too hard, overstressing their aircraft. 1 Zero's wings folded upward, the structure failing catastrophically. The aircraft tumbled from the sky, pieces separating as it fell. The second Zero's wing skin began rippling, buckling from excessive stress. The pilot immediately reduced his G-load, accepting a wider turn that allowed Swett to gain angles. Swett fired a burst into this second Zero, striking its engine. The Japanese fighter trailed smoke and descended, pilot attempting an emergency landing. The remaining 4 Zeros broke off their attack, extending away to safe distance. They'd learned that pursuing a Corsair into a high-G turn was suicide. Swett didn't pursue. He'd expended significant energy in the sustained turn and needed to recover his airspeed. He climbed back to altitude, reset his tactical position, and resumed combat air patrol. 3 Zeros destroyed or damaged, 0 Corsairs lost. The engagement lasted less than 4 minutes. Swett's after-action report noted that the Zero pilots had shown tactical awareness and coordination. They weren't inexperienced rookies, but their aircraft's structural limitations prevented them from executing the maneuvers necessary to counter his sustained high-G turn. No amount of skill could overcome that engineering disparity. This pattern repeated across hundreds of engagements during 1945. Corsair pilots with adequate training and proper technique could consistently defeat numerically superior Zero formations by exploiting structural strength advantages. The data from these engagements filtered back to tactical training units, where instructors incorporated high-G maneuvering into curriculum. New pilots arriving in the Pacific had already practiced the techniques before seeing combat. The psychological impact on Japanese pilots who survived these encounters was documented in post-war interviews. Many Japanese aviators identified American structural superiority as among the most demoralizing aspects of the Pacific Air War. The experience of watching your wingman's aircraft disintegrate because he pulled too hard trying to match an American turn created profound helplessness. Japanese pilots understood intellectually that their aircraft had limits, but experiencing those limits in combat, watching friends die because their planes broke apart, created trauma that theoretical knowledge couldn't prepare them for. Some Japanese pilots developed fear of high-G maneuvering altogether, reducing their effectiveness even further. They'd been conditioned to believe their aircraft couldn't handle aggressive turns, so they flew tentatively, avoiding situations that might stress the airframe. This self-imposed limitation made them even more vulnerable to aggressive American tactics. The Corsair's legacy extended far beyond World War II. The aircraft remained in production until 1952, the longest production run of any World War II fighter. It served with distinction during the Korean War, providing close air support for United Nations ground forces. French naval aviation operated Corsairs during the First Indochina War into the late 1950s. Some foreign air forces flew Corsairs into the 1960s. The design's fundamental soundness, its structural strength and powerful engine, ensured relevance long after more specialized designs became obsolete. Modern fighter pilots at the Navy Fighter Weapons School, Top Gun, still study Corsair tactics. The principles of energy management, structural exploitation, and aggressive maneuvering remain relevant even in the jet age. While specific techniques have evolved with technology, the underlying concepts persist. The story of why Corsair pilots started pulling 7Gs in turns and Japanese Zeros couldn't follow is ultimately a story about engineering philosophy. American designers, with access to vast industrial resources and high-quality materials, built aircraft optimized for performance and survivability. They accepted weight penalties in exchange for structural strength and pilot protection. Japanese designers, constrained by limited resources and strategic requirements emphasizing range, built aircraft that sacrificed durability for capability. Both approaches made sense within their respective contexts. The Zero was an exceptional fighter for 1940, but by 1944, the war had evolved beyond the Zero's design parameters, and Japanese industry lacked the capacity to produce replacement designs in sufficient numbers. The human element remained crucial throughout. The term, Corsair's structural advantages, meant nothing without pilots trained to exploit them. American investment in pilot training, in developing proper anti-G techniques, in fostering bottom-up tactical innovation, transformed engineering advantages into battlefield dominance. Japanese pilot quality declined as experienced aviators died and training programs collapsed under resource constraints. By 1945, many Japanese pilots had fewer than 100 hours total flight time before entering combat. They lacked the skill to exploit even their aircraft's remaining advantages. The combination of superior American equipment and superior American training created an insurmountable gap. The tactical evolution from avoiding zero-turning fights in 1942 to actively seeking them in 1945 represented one of the Pacific War's most significant shifts. American fighters went from disadvantaged to dominant in just 3 years. Lieutenant Robert McClurg survived the war with 7 confirmed victories. He remained in the Marine Corps until 1965, retiring as a colonel. In his retirement writings, McClurg emphasized that while high-G tactics improved Corsair effectiveness, they never made aerial combat safe or easy. The technique eliminated one variable in the combat equation, but countless others remained. Altitude management, energy state, situational awareness, tactical positioning, ammunition conservation, all still mattered critically. A pilot with perfect technique could still be outmaneuvered, outclimbed, or simply caught unaware by an enemy he never saw coming. The Corsair gave pilots tools to survive and win, but it didn't guarantee anything. Combat remained lethal, demanding, and unforgiving. The pilots who mastered high-G maneuvering were those who understood its limitations as well as its capabilities. They knew when to use it, and when other tactics were more appropriate. They maintained awareness of their own physiological state, recognizing warning signs of impending blackout and backing off before losing consciousness. They coordinated with wingmen, ensuring mutual support during vulnerable high-G periods. The F4U Corsair achieved an overall kill ratio of 11-1 during World War II, destroying 2,140 Japanese aircraft while losing 189 Corsairs to enemy action. These statistics represent combined results from all Corsair variants across the entire war, encompassing thousands of engagements under varying conditions. Separating the specific contribution of high-G tactics from other factors like improved pilot training, numerical superiority, and declining Japanese opposition quality is impossible with available records. What can be stated with confidence is that Corsair pilots consistently reported that their aircraft's structural strength provided significant tactical advantages, particularly in situations where sustained maneuvering was necessary. The ability to pull harder sustained turns than enemy aircraft could match gave Corsair pilots options that earlier American fighters lacked. This capability, combined with speed, firepower, and ruggedness, made the Corsair one of the war's most successful fighters. The Japanese never developed an effective counter to American high-G tactics. Their industrial base couldn't produce fighters with sufficient structural strength to compete. Their pilot training programs couldn't maintain the quality necessary to exploit tactical innovations, and their strategic situation, with supply lines severed and resources depleted, prevented them from implementing solutions even when they understood the problems. By mid-1945, Japanese fighter aviation existed primarily as a kamikaze force. Conventional air combat had become impossible. The structural disparity between American and Japanese fighters was one factor among many contributing to this outcome. But it was a significant factor, removing Japanese aviation's last remaining area of advantage. When Zero pilots could no longer rely on superior maneuverability, they had nothing left to work with. The Corsair program represented American industrial and engineering capability at its peak. The aircraft incorporated cutting-edge engine technology, innovative structural design, and rugged construction. It was manufactured in quantities sufficient to equip dozens of squadrons, distributed across a global supply chain, and maintained in forward areas under primitive conditions. The program succeeded not because of any single innovation, but because the entire system functioned effectively. Vought engineers designed an exceptional airframe. Pratt & Whitney produced a powerful, reliable engine. American factories manufactured components with precision and quality. Logistics personnel delivered aircraft where needed. Maintenance crews kept them operational, and pilots used them effectively in combat. Each element was necessary. Without any single component, the program would have failed. The final assessment of high-G turning tactics must acknowledge both what can be documented and what remains uncertain. Combat action reports confirm that Corsair pilots used sustained high-G turns effectively against Japanese fighters. Pilot testimony consistently describes structural strength as a significant advantage. Japanese tactical directives ordering avoidance of sustained turning fights with American fighters demonstrate that Japanese command recognized the problem. But precise statistical analysis of how much high-G tactics contributed to overall Corsair success versus other factors is impossible with declassified records. The 11-to-1 kill ratio represents comprehensive performance across all variables. What remains clear is that the Corsair's 8G structural limit, combined with pilot training in anti-G technique, provided tactical capabilities that Zero pilots flying 6G limited aircraft could not match. This advantage was exploited consistently and effectively by American pilots from 1944 through the end of the war. The story of Corsair pilots pulling 7Gs while Zeros couldn't follow is the story of engineering meeting combat, of industrial capacity enabling tactical innovation, and of trained pilots exploiting every advantage their aircraft provided. It demonstrates that weapons systems succeed through the integration of design, production, logistics, training, and employment. The Corsair was an exceptional fighter not because of one feature but because every element worked together effectively. The structural strength that enabled high-G maneuvering was just one piece of a larger system, but it was an important piece, one that helped transform American fighter aviation from defensive in 1942 to dominant by 1945. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.